Oh, yeah.
No.
Want me to hide it?
No, just kidding. Okay. So homework 4 does exist. I didn't upload it on Monday or Tuesday because I was in a science team meeting and I was overwhelmed. What happens? You know, like Bilbo with the ring spread over too much toast? That's me.
Wait.
You know how you feel like what you're spread over, like butter spread over too much toast? Very thin, spread thin. That's me, my intellectual state this week. So instead, I finished the homework last night. And I thought, you know, everyone was like, oh, we really like when the homework is due on Wednesday. So now the homework is due on Wednesday again. So this one will be due a week from today. Okay. And so we'll post it later on. And this is the content we'll be talking about. So we'll do a quick recap of how we think about gases and whatnot. And then we'll directly start applying them to planetary systems in understanding this thing that we're walking through right now, which is an atmosphere. Okay. You want to hit half the light, Susan? Nope. 1.5. Nope. Other half. Thank you. Okay, so what's this thing? Earth. Okay. More information?
Atmosphere.
Okay. Atmosphere. What else do you see in the atmosphere? Clouds. Cloud. Okay, very good. And you see that some of these clouds have vertical structure. So we sit on the earth and we look up and it looks really flat, but you'll see this is an altocumulus cloud. This is a rain cloud or a thunder cloud. And they're called anvil clouds. And you see what that's happening here is just a huge column of rising moist air. And as it cools, it condenses, and then you get rain. And so you can see the entire atmosphere here. You will notice that the earth is in fact
Round.
it's round in this photograph. This is taken from the ISS. Remember when we saw that picture of Titan? And I said there were liquid like oceans on Titan. And I said you could see that because there's this backscattering off of the ocean. So this is the same orientation. The sun's over here. It's in this direction. This is the terminator. I don't know if it's dusk or dawn, but this is the region where you'd be seeing sunset. So if you're sitting here and you're looking in that direction, you're going to see a red sky. Whereas from this direction, it's very blue. And we'll talk about Rayleigh scattering, not this, maybe in like 3 class periods. Okay, so for folks arriving right now, there is homework 4. It's due a week from today. So you have time. Okay. So we're going to think about light as an information bearer. This is how we get a majority of our information about things that we cannot visit. So all stars, but this also includes planets in the solar system. And I made a claim that this is an object. It's an object in our solar system. And I'm going to tell you how you would figure that out based on this similar picture. And in fact, you may have a homework problem that presents you with a spectrum and asks you to make changes to it based on what a different object would look like. Okay? It won't be perfect, like you won't be asked to put exactly the spectral lines in, but you'll make broad changes to it. Okay? So we can tell the composition. How can you tell the composition of something? Spectrum, okay? Another way of saying that.
Color spectrum.
So the color spectrum, right? Like if there's rainbow here, does that tell you what's inside it? No. Emission, right? Emission tells you what's inside. What's another way that we know? Absorption. Absorption and emission both tell you inverse processes, right? So the presence of line here, these are emission lines. And then the absence here, these are absorption lines. And they're both telling you something different. Okay? It can tell you the temperature. How does it tell you the temperature? By the color? Yes, okay. Right, so it tells you 2 things. So for example, if I heated an object up, if it was the same object, the color would tell you. But here, specifically what I'm talking about is where the peak of the continuous distribution exists, right? And that's another way of saying color, but we want to be specific about it. Because if this same thing here, right, let's say this is moved over to the left, then I would say that is hotter or colder? Hotter. If it's moved towards the blue, it's hotter. And if it's moved that way, it's Colder. So in fact, I see two continuous emissions, right? One here and one here. Which is hotter? This one, right? This one's so hot, it peaks where? Yeah, so that's in the visible. So this must be what? The sun. Oh, snap. Okay, except something special is going on here. There's a missing part. Uh-oh. Oh, no. Okay, we're gonna get to that in a second. We're gonna talk about velocity, but not yet. We'll need to understand the Doppler shift in order to do that. Remember that there are three types of spectrum. So how do I get a continuous spectrum? Yeah, how do I get white light? That is how I get all the colors in white light are the same. How do I make it? I want to make it at home. What?
Put a bunch of gases together.
Hot dense gas. So for example, if I heat up a piece of metal, or if I heat up a ball of gas that has many species in it, right? Like the sun, then I can get a continuous source of light. Candlelight, for example, probably going to be more continuous. Emission lines. What's that? Hot thin gas, okay. And what's the orientation that I'm looking at this in? So let's say I have my gas, it's in my hand right here. Okay, if I place it like that. No, why not? Because that will be absorption. That will be mostly continuous. Imagine that that's an incandescent bulb. As it comes through, some of it will get absorbed by the gas and it'll not make it to my eye. Whereas if I stand like this, okay. If I stand like this, right? Dark background, it's being illuminated, and now the gas is going to give off the light. So that's the emission line spectrum up here. Okay, so let's walk through that again with the actual pictures instead of just me talking. There we go. So there's the continuous spectrum. You take a really hot solid or dense liquid, and it will emit a continuous rainbow. Okay. That's called black body radiation when you take quantum mechanics. One of the reasons that they prompted quantum mechanics at all. Because in order to understand why this is happening, all of the energy levels have to be quantized. Okay. We're not going to get into a lot of this. Why is this doing this? All day long, this is giving me grief. There we go. What?
You batteries?
No. Oh yeah, maybe. That's probably smart. Okay. So we talked about atoms and molecules. And atoms can be very complex, right? Like oxygen is quite a complex atom, or they can be very simple, like hydrogen. The important part here is that, for example, oxygen can change levels in the electron. So the absorption and the emission of light changes the energy levels in that atom, right? Molecules do the same thing, but they can do sort of weirdo ones. So for example, hydrogen can be here, but it can also go back and forth like this, like a spring. So there's a bond between oxygen and hydrogen, and that bond can flex. And it turns out the flexing of that bond can be induced by microwaves. That's how it heats up your heats up your food. Gonna blow my brains up today. Okay. So water's a molecule, and H and O are atoms, right? Okay. And so this is how you get this emission line spectrum. So you pump these things full of energy, and we saw this on Monday, right? So what we did is we heat up the gas, very hot gas, and it lets off these specific lines. So carbon, nitrogen, and neon, which of these has the highest atomic mass unit? Does anyone know what that is? Of these three.
Oh.
Neon. Neon is, yeah. So neon is the largest. It goes carbon, nitrogen, neon, and then of course magnesium. Magnesium does some other funny stuff, and so it doesn't have as many lines in the visible as neon does. Okay, and if you've seen a green neon lamp, what's the response?
No.
No, you haven't, right? What color is neon?
Orange, red.
Orange, red, right? That's like the typical neon sign. Everything else is neon plus something, or no neon at all and just a different gas. Okay, but we love butchering words in the English language, literally. Okay. So the third one here is the emission spectrum. Or sorry, the second one here is the emission spectrum. This is what you see when you just have a cloud of gas. And of course, if you imagine, you're just looking out into space, you don't always, it's not always so convenient that there's some star or a giant lamp behind the gas you want to look at. So more often than not, this is what you are going to see. You're going to look off in a direction, and it'll just be hot gas living on its own, right? And so you get this a lot. And this will tell you what's inside of it. And then this one, we already talked about it. Finish this up today. Hot light source through cooler gas. And the example that I showed both in the middle of class and at the beginning of class last time was
The sun through the atmosphere.
exactly right. Oh my gosh. Guess I'm not moving. Okay, there we go. There's the solar spectrum as seen from the Earth. You have to have a very good spectrometer, right? Something that can resolve all of the light really well. This here is the sodium doublet. That's all you care about, but there's other lines in there too. Okay. Pretty cool, right? Lots of structure. So each one of these represents a different atom or molecule. Probably not molecules because it's 5,000 degrees, but usually a lot of atoms in the upper atmosphere of the sun. If you're in the fluids class, you saw that these particles here, they don't escape. They form an atmosphere above the surface of the sun. Okay. Feel like you get it? Feel like you can do it on your own? No or yes?
Yes.
I don't wanna do it.
I don't wanna. Okay, you get the lights. Make a new friend. Okay. Mix it up. Who are you? Maybe your friend. What? Make a new friend. You have a friend. What? Oh, okay, you already gone. Who has two in their group?
What? A paper?
Someone has two papers in their group. Yeah, someone has two papers in their group. Okay, so pass that paper back. Yeah. Have you guys worked together?
Yeah.
You guys work together? Do you guys work together? Have you guys worked together? Do you work together? Do you work together? All right, well, that's what happens. Saley, you want to go back with him?
Yeah.
Okay.
Yes. I just don't want to be. Yeah.
Are they? Oh, I was like, yes. Oh, this one. Oh, the main side. The last one.
I mean, these are basically good peanut butter.
What kind?
Oatmeal peanut butter?
Go.
That'll work.
Yeah. What?
Yeah. Switch more sense.
But no, what else is? How do you get in the front?
Far away stars. Or yeah, wasn't it fifth many to like the 7th Street? Yeah. This is first round. Lotus. When it comes to storage, I'll turn out to be like, yeah.
Hot and then should be cold. Or.
Need the caramel. Does that make sense though?
No, it's not. I think those ones that got you out of the one.
Yes, for next week. Pepper line.
Yeah.
Do you remember that one? I think we used a pencil and a string, or pins into cardboard and a string. To make the letters, right? I might send that to you, or you can pull it up this weekend. It's not as tricky as the Earthquakes one, but it's certainly one that's like. It's more drawing.
I'll figure out.
You have three, right?
Kobe was.
You done?
Yeah. No, I gotta take it like that. That would be. Oh, damn. This was.
Good.
Are they, you never the hall? I thought it was kind of like. Yeah.
I gotta say it's good. That's just looking at the moon, it's funny, and it doesn't have an atmosphere. It'd just be. Cause it's not.
Which one is?
It's.
Okay, yeah.
And then it's like. It's just right. Is that a mission?
Thank you.
Like, it's like.
If anyone else has 3 too. 3 as well.
What? Oh, the atmosphere. Oh, yeah, because, you know, comes from
Sun around?
the-
Which?
something fertilizer.
That powered by the sun. Oh.
Yeah.
Yes.
This one.
It's just being instead of make out with yourself.
You want to focus on the
Or training this way, our four process. Don't pull me. It's up.
Yeah. You're planning on having. That's all.
Easy.
Yeah. Are you planning on 300?
Astro or? We can find out when I reassign the time. It's the physics of the so it's like this guy, but it's significant.
33 or 3310. 3300 hasn't been offered in a while.
Yeah, 3300, I think I taught last now, the show, or maybe. How many years have I mentioned? Spring. No, fall 2021.
I want to put this down on like planning.
Easier to
Yeah.
Is that?
I don't know one volume.
You already I didn't even notice. Oh, that?
Yeah. I forgot the only as well.
Okay, folks, let's find a good stopping point. All right. If you have any homeworks, you can turn them in. Okay, so now let's go back to this thing that I promised that we would be able to do. Okay. Let's use information in here to determine what are we looking at. What do you see? Peaks. Okay, where do you see peaks? Down? Here? Okay, so there's something peaking here, okay? Another peak. There's another peak. Okay, good, good.
Solar flare.
Where do you see the absorption spectrum? Where?
On the rainbow.
Here. Oh, yeah, and look, that kind of correlates with the stuff above it, right? So I've written intensity this way, but you kind of get a measure of the intensity in the colors. And the absence of colors here is seen as little lines. So that's supposed to be an absorption spectra, right? Okay, anything else? Where's the emission spectrum?
No.
Right, way over here. So these are emission lines, absorption lines. What was this big hump called? Continuous. So there's all three of them are here. Except this one looks a little funny, right? Why does it look funny? Well, it's still just look at this one here. Not the one on the right. Why does it look funny? It doesn't look like this one on the right. Move to the left. Right? Look at the colors here. Blue, green, and red. Is there as much blue as there is red? No. Huh, that's weird. What about this thing over here? What color is this? Infrared. What does infrared mean? Heat. So this is emitting in the infrared. So this must be a source of its heat. Oh, interesting, interesting. Okay, so what is this object? In fact, this is thermal emission from the sun. And this is the source that is either absorbed or reflected. So notice that it's not complete. So, for example, right, if I put my hand out here, you see my hand, some light does get absorbed, right? Some colors more than others, right? But this is the sun's original spectrum. Okay? So what's the object? Let's look over here. Oh, there's supposed to be words there? Yeah, they're there. Whew. Okay. So it's got to be a solid object. All right? Or at least a really hot gas. But the hot gas over here has a temperature that corresponds to 225 Kelvin. I'm telling you that. Okay? This is a thermal peak. Okay, anything else? Well, we saw over here infrared absorption lines. That's what's happening in these places. This is where CO2 likes to absorb. And finally, ultraviolet emission lines. So it has a hot upper layer of gas. Nope. It's not that hot. Remember that this is reflecting sunlight. So it has a hard surface and it reflects sunlight, but it reflects less of one color than other colors. Solar flare? That's not reflecting sunlight. So you have two objects here, right? This is reflection from the sun off of the object. This is the temperature of the object itself, 255 degrees. There's two peaks here.
Is there an object passing in front of another object?
This is one object. But there's two processes going on.
Water.
Well, there's four processes going on. Here is emission. Here is absorption. But this is broad absorption. What's that?
Is it Mars?
Yes. Why is it Mars?
Red?
Because it's red. Why was it red? How did you know it was red?
Because it passed more red off of it than the other colors.
Exactly. Remember, this is the reflected light from the sun. If it were white, the whole thing would go down a little bit, but you still have the same shape. So if I ask you to make a blue object, where are you going to cut it? Yeah, if you start off with a spectrum that's the sun, and I ask you to show me the spectrum of a blue object, reflected sunlight off a blue object, what will it look like?
You're gonna cut the green redstone.
Yeah, you're gonna cut it the other direction, right? Now I get it. Now this makes perfect sense, right? thing's never gonna work. Screen. Yeah, that's smart. Okay. Acceptable answers include Venus, but it's not what I meant.
So that infrared that we see is the heat that's coming off the sun hitting our then back to.
No, so this one's different than this. This is a reflective and absorptive process, right? We thought about the 4 different things that can happen to light. It can be emitted, be absorbed, be reflected, and can be transmitted, right? So this is the reflected sunlight peaking in a place that we can see. This is the heat that Mars gives off, because Mars is not 0 degrees temperature, right? So on the night side, for example, how would this look different?
Pretty much get rid of all the yellow and then just have some red.
Yeah, all of this would be gone because you can't see it. You'd only have this, right? Maybe you have a little bit of this. Is that intuitive yet? Okay, that's fine. Okay. So in general, we're going to talk about planetary atmospheres. There's some major questions that we'll want to think about. We live in an atmosphere. How did it end up so different from any of our neighbors? Are humans changing the planet? Show of hands. Yes. Anyone disagree? Maybe we'll skip that lecture. Okay. Don't need to tell you. Okay. Does Saturn have a surface?
Yeah.
Yeah.
Okay. All right. We got some choices here. Yes or no? You guys want to fight about it?
Yeah.
Which one?
Oh, okay. We're gonna get to it. The Saturn.
Which side of that?
Which side is that? Okay. No. What happens if you add more mass to Jupiter? You get bigger or smaller?
Smaller.
Okay. All right. All right. Interesting. So let's talk about planetary atmospheres really quickly. We want to think about what an atmosphere is. We want to think about how a greenhouse effect warms the planet, and this fundamental question that every 2-year-old asks: why is the sky blue? How many of you have asked that question? And how many of you have felt like you've understood the answer?
I understand it, I forget it.
Right away, right after I forget it. So the goal of this class, and the goal that you have for the entire semester, is just this. Just to be able to explain to a 2-year-old why the sky is.
You're 3.
And they 3? Too many questions. Say no. Okay. So which of the following is the lowest layer of our atmosphere? Is it A, the lithosphere, B, the exosphere, C, the stratosphere, D, the troposphere, or E, the thermosphere? Hey. Let me know when you're ready. Let's vote on 3, 2, 1. All right. Okay, I think people thought this was funny. Not part of the atmosphere. What is the atmosphere?
It's in the lithosphere.
The atmosphere is in the lithosphere?
Oh, no.
What's the lithosphere?
Outer surface, the inner, the outer surface, what we're on.
What we stand on is the lithosphere. It's the coolest rock at the edge of the planet. What's the exosphere?
It's right outside.
It's the exterior of the atmosphere. Stuff in the exosphere, if it gains enough energy, it will simply leave and never come back. Down here, you can energize atoms all you want, and they just get hotter and hotter and hotter. They don't try to leave. Stratosphere.
Next layer down.
A lot of people like stratosphere. Incorrect. Stratospheric clouds are above the troposphere, which is where we live, and the thermosphere is above the stratosphere, and we'll see all of this.
All these words were used in order.
I know, but you're gonna have to figure them out. What does thermosphere mean?
That keeps
Thermal.
Where it's hot. No, there's, well, depending on how you want to cut it up, yeah, there's about 4 layers. Okay. Okay. Can you hit 2 of those lights? Darn. Okay. On the left-hand side, you have Mercury, Venus, Earth, Mars, and the Moon. And they are in the correct sizes relative to one another. So what do you see in this picture?
Earth is the biggest.
Earth is very slightly biggest, yeah.
Moon is not.
Why is Mercury not full? I'll get a better picture. Next year it'll be full, okay? Let me write that down, Kobe. Anything else?
Moon is the smallest.
Moon is the smallest, good. Earth is flat on this picture.
Oh, no. Cloud.
It is clouds.
We can debate about that about Venus. It's like a square kind of looking.
Yeah, what is that? You see that?
The moon and Mercury.
That is an actual object on Venus. There's super rotation. So this is a really, really quick rotation way up in the atmosphere, dragging clouds along. You can't see the surface on Venus, and you can kind of see the surface on Earth. There's some fun like rotating parts, and there's just this weird V thing on Venus. What about over here? You can see right to the surface. Doesn't look like there's any clouds. Very boring looking, right? It's not. It's cool. All right. Don't write this down, but this is something we're going to think about. So you have the Moon and Mercury, losers of the inner solar system. Rock vapor. What does that even mean? Solar wind stuff? That's barely even a word. Look at this pressure. 10 to the minus 15 bars. So this is the pressure. What's a bar?
16.59.
Yeah, what do you what's the reference point for a bar?
Like Earth.
Yeah, it's the Earth. The Earth pressure at sea level is a bar on a typical day. So this is 10 to the 15 times smaller than that. So you can have a good time on the Moon and Mercury? No, in fact, if you take your spacesuit off for any reason, your blood simultaneously freezes and boils. Fun, right? Okay, Venus. Now Venus is a weirdo, okay? Venus, the composition here, look at this, 95% CO2. Very similar, sorry, 96% CO2, very similar to Mars, which is 95% CO2. But look at the major difference here. I just told you that this is the pressure, okay, at sea level. This is 90 times the pressure at sea level. Yeah, not gonna have a good time, okay? So what happens at 2 bars? Well, as you swim down into the ocean, right, you feel like uncomfortable and you have to kind of let out air or you get the bends. Every, I think it's 10 feet or 10 feet that you go down, you get about an extra atmosphere of pressure. So this would be like going down 900 feet. People don't live down at 900 feet, but whales do. So maybe a whale will be okay. Okay, hold on, calm down. Okay, and over here you'll see. Yeah.
Is bar macram something that is below
Oh,
atmospheric?
barrels.
No, it's an actual term.
Okay.
Oh, and look, it's written right there. Oh, interesting. It's almost like I prepared for this. Okay, and so here you'll notice the composition, nitrogen and CO2. But Earth is a little unusual, right? Because every time you breathe in, you're breathing in.
Wait, no.
Oxygen.
That's a plant.
Everyone says oxygen, but what are you really breathing in?
Nitrogen.
Mostly nitrogen. Because oxygen is actually quite flammable. So if it was just oxygen, the whole world would be on fire. And that's not good.
Like Venus.
What's that?
Venus? Oxygen.
Not to us.
Yeah, too much.
Oh, yeah. Of course, if you have too much, right? You want to have like this mix. Because you don't want to die. Okay. Okay, so this is the atmospheric composition. And here's a question. Are we at more, less, or equal to 1 bar at the top of the press line?
Press line is like that. There you go.
That mountain right there. Vote on 3, 2, 1. Okay, I think we got every answer here.
But only one is correct.
Does anyone want to defend their answer?
Okay.
Yeah.
Well, I know, like, you know, if we go higher in elevation,
Mhm.
the pressure decreases.
Okay. What's an example? Like, how do you know that?
A balloon, like, I guess, like, you know, like, if you were like driving near like San Bernardino,
Mhm.
and you know, have like a
Mhm.
from like, helium,
Mhm.
if you go up, it'll.
Okay, yeah. Or like the bag of chips in a plane, right? Or like if you go up to, a lot of people have been to Mount Everest, right? And so then you have to wear your. No.
Oh.
So of course, it's this one here, less than 1 bar. Okay? And in fact, on a day-to-day basis, the temperature will vary and that will change the pressure slightly. But for the most part, elevation, at least in the troposphere, is telling you how much pressure you have.
I thought it would be more because we're up, further up to the zero. That's like an option. So we're lower. There's less pressure pushing on you.
Yeah, so here's the question. What causes that pressure? We're gonna talk about that in a few seconds.
Do I have to?
Yes, yeah, you always have the right to be confused. No one's allowed to not be confused. Okay. So let's think about the atmospheres in the big picture. Mercury and the moon, we're not really gonna talk about. We'll mostly talk about Mars, Venus, and the Earth. Venus has a huge pressure, Mars has small pressure. Venus is too hot. We already said that the surface temperature there is something like 700 degrees Fahrenheit. So that's like not chill. And Mars is too cold. So a lot of people have this misconception that, you know, if they were to go to Mars, that it would be like a desert. They see the red rock and they think Utah and they think it's gonna be hot. And in fact, it is freezing, below freezing the whole year round. And only a very small portion of the year, at very specific locations, do you ever get above and just slightly above freezing. Okay? Earth is strange, right? So based on what we see here, it's the odd one out. And we want to understand why that is. Okay. So what are reasons why the atmosphere should not matter?
Doesn't matter.
Yeah, well, I'm gonna do that in a second. What are reasons that it shouldn't matter? Yeah, why wouldn't you care about an atmosphere? I have lots of friends who don't care about atmosphere, they're jealous. Like, they can't about atmosphere. Why shouldn't it matter? Never thought about that?
Cause mass extinction.
Okay, let's rephrase this. Okay?
Thank you.
That's in every word. Okay, the mass is tiny. It takes up a very small fraction. Right, we said that if the Earth is the size of a basketball, the whole atmosphere is the size of a sheet of paper. You'd say, well, why would you spend as many weeks in the atmosphere? Right? The atoms themselves have negligible mass. Right? But of course, we know why we like the atmosphere. What are your reasons for liking the atmosphere? We like it, yeah. We all live in it. Good. Anything else?
You bring Texas.
What kind of scary stuff? Rock, yeah, rocks coming down, burn up. UV rays lets me get a nice suntan without getting skin cancer too much. Traps the air here, which we breathe. That's good. Anything else?
Get a blue sky.
Blue sky, beautiful at night. Sunsets. Ooh. Okay. Anything else? What about like wind? Anyone like wind? Yeah, like windmills necessary for like a really long time. So we discovered like, you know, other forms of electricity generation. Okay. Sails, you know, used on the push boats. Okay.
What year are you?
In the 1600s, isn't it obvious? Okay, so we're gonna talk about most of these here. We'll talk about the greenhouse effect. This artificially increases the temperature at the surface. In the same way that when you get into your car on a hot day, car's hot. We'll talk about scattering and absorption of light, how this one concept, the scattering and absorption of light, will tell you everything about the thermal structure in the atmosphere. So if you can just understand what type of light is absorbed at what type of frequency, by who, you get this whole piece. Okay. You'll understand why the sky is blue during the day and red at night. You'll understand how there's weather. And we'll understand, of course, first how it creates pressure. Okay, so why do gases have pressure in them? Or what causes a gas to have pressure? What's that? That's another word for a similar phenomenon, but what's going on in the gas? What's that? The volume. Okay, so these are words that describe the thing, but what happens inside the gas that causes there to be pressure?
You know, like the, I don't know, like,
It's like, in the mentor's office?
Okay, everyone at the same time, one name, go ahead.
so like the atoms are hitting each other and they're like bouncing off in all directions so that they
Right.
essentially force the pressure in all directions.
Right, so there's an actual, inside of a gas, individual atoms are bouncing off one another. Right, and it's this bumping into one another, whether it's violent or, a lot at the same time, it would be hot. Versus if they're moving very slowly and the collisions are happening less forcefully, it would be cold. Okay. So we look inside of a balloon, and of course, this is an exaggeration. Inside of the balloon, the pressure is balanced, right? Because on the inside, I just blew in this air, had it blow up. On the outside, as many molecules and atoms are bouncing off the outside as there are on the inside, and so the shape of the balloon doesn't. This is the idea of pressure. Okay. Okay. Come on now. I know this. Okay, which of the following does not increase the pressure inside of a balloon? A, heat up the gas inside the balloon. B, put more gas inside the balloon. C, shrink the size of the balloon. D, take the balloon up to a higher altitude. Or E, all of the above increase the pressure inside of a balloon. Let me know when you're ready to vote. Vote on 3, 2, 1. Okay, all right. All right, why don't you turn to your neighbor? Specifically, look for someone who didn't get what you got and ask them why.
Yeah. I don't know what happened to that. And then the special side. Yeah.
But it's so great. Yeah. Yeah, but we're.
Back row, you ready? It's a timing gate. So stuff goes through, it goes on and off.
Like the disinfectant.
Okay, we ready? Okay.
You know this when you hired me.
She loves ghosts. Okay, let's vote on 3, 3, 2, 1. All right, there we go. There we go. A lot of folks liked 4 now, where they liked 5 before. What happened? Yeah.
The balloon container is flexible, so the pressure inside the balloon does not change, it just matches the pressure on the outside when you change elevation.
Right. So as you go up the hill, the pressure goes down. And in fact, the pressure inside the balloon as you went up the hill would go down, especially if you go up slowly. Right? You go up slowly with the balloon. At every moment, the balloon is just getting slightly bigger to match the outside pressure. If you take a balloon You put it under water. Press on the balloon, make it smaller. Well, first it'll try and get away. So you gotta be really careful. If you never put a ball underwater, it goes. But if, for example, if you take like a submersible with human beings in it, that air pocket in the middle, you put it too low.
Submarine.
What?
Submarine.
Yeah, like a submarine. Okay. So we can add more gas. If I increase the number of particles, I can get the pressure to go up. If I heat the inside, I can get the number of particles to move around more violently. We talked about temperature in that respect, okay? And if I pressurize it, right, I can squeeze them into a smaller space. This will make the pressure go up. So the same number of particles in a smaller space is going to make the pressure go up. And so what we have here is that you have all of this stuff up here presses down like Princess and the Pea, right? So the Pea is down here, Princess up here, right? And all of those pillows make this part squished and flat. Pea would be squished in that story, that's true. Yes.
Yeah, I'll leave it.
Yeah, let's not do story time in class. Okay, so we have a real atmosphere here, and the pressure at the bottom of the atmosphere is due to what? Squish? Okay, that's one way to think of it. It's only due to the column of air above it. So if I'm up here and I look above, there's very few particles, right? So the pressure must be low. As I go deeper, that column of particles that's holding me down gets bigger and bigger and bigger, and that pressure gets heavier and heavier. The same thing is true, because if imagine this is an ocean, and now I go into the ocean, right? The very top, pressure might be whatever. So I go deep in the ocean, it gets much higher because there's a column of water that's crushing, right? Just like the P at the bottom here is crushed by all the pillows. Right? You did it. So now we know why we go up mountain. At the top of the mountain, the pressure isn't. You're not getting crushed as bad. Okay, so let's talk about the surface temperature of planets, right? We care about that because that leads to how warm we are in general. The sun gives off mostly blank light. The Earth reflects some, absorbs some, and re-emits blank light. Fill in the double blank. Let me know when you're ready. Let's vote on 3, 2, 1. I got all of them. I got all of them. Let's go, baby. All right.
Is this your goal?
Yeah, I like creating questions that make people think.
You like-
Okay. So I got an answer for every single one. And in fact, only one answer is correct. So let's turn to a new friend and ask them what they thought. See if you can convince them of your answer. If you think you're right.
I don't know if I'm right though. And that's why we think it's
Let me To see what the sun is. One color. I guess. And it's pointless. It's really long. You notice that like how it was like reflected sunlight and.
Okay, we ready? Ready for a revote?
Yeah.
Show me your fists. Let's revote on 3, 2, 1. Okay, all right, we had some conversion. So who likes A? Who likes B? Okay, you want to explain B for me?
I'm just thinking, the atmosphere is what covers us from the ultraviolet.
Mhm.
So the sun gets that off, and then
Yes.
when it comes to the earth, after it goes through the whole atmosphere, that's where we get to see the visible light to us.
Okay, so there certainly is ultraviolet given off by the sun. But the predominant amount of light is given off in the visible. So we see in the visible, there is infrared and there is ultraviolet given off by the sun. But since I said mostly, it's these between these ones.
Yeah.
Okay, so it's true that there is ultraviolet. Okay. So then the second part is the earth reflects some visible light. It absorbs some visible light, right? That's what makes the surface hot. The question is what kind of light does the earth re-emit? Why the infrared?
It's heating up.
Okay, people don't like visible? Yeah, you like visible?
Yeah.
Why visible?
I think it's blue. It's losing a visible light, so.
So is the earth emitting that blue light or is it reflecting the blue light right here? Yeah.
I think it re-emits the infrared because it has heat,
Mm-hmm.
so I think it emits.
Yeah, what's the difference between emission and reflection again?
Like, it's like it bounces off,
Reflective bounces off and emission is?
you mean like absorb it and then like.
Okay, hold on. So in getting rid of it, remember, emission doesn't have to be absorption. We do not need to mix these, right? I could be radioactive, right? Oh, the earth inside is radioactive, very radioactive. That's why hot. No.
Yeah, I thought it was just.
Okay, so in fact, the earth, the sun gives off mostly visible light, right? And that's why we see in the visible. The earth reflects some of that visible light. It absorbs some of that visible light. For example, in the ocean, it reflects blue light and it absorbs everything but blue. And it re-emits infrared light, because if it were emitting visible light, we would all be in grave, grave danger, right? Why would we be in grave danger if the earth was emitting visible light? What? Just a hand, please. Yeah. Worse than that.
Be extremely cold.
Nope, worse than that.
It would be like hot, like sun.
Exactly. It'd be really hot. So if we're emitting visible light, then we're really warm. So I'll give you an example of a rock type that emits visible light. Lava. Right? Lava, hot, red. Right? And then when it cools down, what color does it become? Black. The absence of giving off light.
Like body.
Bada bing, bada boom. Okay, so now we fully understand it. We're absolutely super confident in every single way. Everyone feels exactly the same way. No one's shaking their head in disagreement. What a great lesson. Okay, so over here, I have my 310K human. That's me. And over here I have the sun. Notice that it peaks in the visible, but there's still plenty of ultraviolet light, right? If I'm floating around in space, this stuff is pummeling into me and giving me a sunburn. Probably just cancer right away, instant cancer. And over here, there's plenty of infrared as well, right? But this is where the peak is. Most of the light is visible light, right? And notice as I make it hotter, that peak moves to the ultraviolet. So whether or not life could exist around an ultraviolet peak star is unclear, right? We don't know. That make sense? What's that?
It would depend on the planet, right?
Right, how thick the atmosphere is, everything like that. Okay, so we are going to use these two ideas together. We said already for Mars that it is absorbing some of this visible light and reflecting some, but it's also emitting way over here in the infrared, right? And this is kind of what it looks like. So for example, you have incoming light in the visible, that's the yellow. Some of it gets absorbed into the surface. Some of it bounces off, and that's how we see it, right? But that absorbed light heats the surface. And in order to get rid of it, the only way to get rid of it is to radiate it to space, right? That is infrared radiation due to the fact that it's hot. Okay? So incoming light illuminates one direction, but the whole planet is illuminated in its own infrared light. Does that make sense? Okay. So this is what it looks like, not for Mars, but for, oops. Okay, there we go. That's Saturn. The red is in infrared here, and this is the visible image laid on top of it.
Wait, so red hotter?
Red hotter, yeah.
Okay, so it's bad again.
So it's what?
It's bad again.
Why is it bad?
The blue hot.
Well, no. On this side, so dark is cold and red is hot. On this side, this is the visible image of Saturn, but I overlaid it on an infrared image. Yeah.
Are those lines shadows?
Exactly correct. So this is the ring right here, and this is the shadow of the ring on Saturn.
Yeah.
Isn't that dope? And in fact, what you can see behind it here, all of this is heat from the interior coming out, shining through in the infrared. Yeah.
What are the rings? Are they gas?
Don't just wait. The rings are made of metal and they were given to Saturn by God, obviously. Put a ring on it. If you like it, then you should have. Okay, so you'll see you'll see here that there are these are all like line-ish, right? We call it line-ish. These are banded. And as we look at the structure of Jupiter, you'll see that as well, that there's banding in the entire planet. And these places that it's coming up and being bright, that happens to be in places where the banding is passing by one another. The picture is going to look a lot better when you download the slides for yourself later. Kind of gets shitty up here. I'll get better pictures, yeah.
Are the dark spots cooler gas?
Yes. Yeah. Yeah, so on this side, cool, hot, cool, hot. On this side, visible light. So this is trying to look like that. So they're connected. Actually. Okay. Let's talk about the structure of a planet's atmosphere. I'm going to make a really bold claim. Okay. I'm going to say that if you can remember this, then you'll understand the entire structure of the atmosphere. And it's fairly straightforward, but it'll take a few seconds to digest. Okay. So at the very top, you have the most energetic form of light, right? That we're going to consider today, X-rays. The sun gives off X-rays. Okay. That's why you don't want to hang out near the sun for many reasons, but this one. So X-rays love to look at small molecules and just break them apart and ionize them. Whatever you were, you're not that thing anymore. Okay. Water, now you're just protons and electrons. Fuck it, right? Ultraviolet really loves to just break apart molecules. So water, ozone, it's like, okay, now you're 2 oxygens and 1 oxygen, right? So in fact, you may have heard about something called the ozone layer having a hole in it. So this is really scary for a while. Ozone, 3 oxygens all sitting next to one another. They love to absorb ultraviolet. And we started putting stuff in our hair when we had hair, like 40 years ago, that had something in it called a CFC that loves to eat ozone. And suddenly there's a massive hole in the ozone layer, and ultraviolet light was beaming down on the planet. And people were like, that's not good for anyone who lives underneath it because they're gonna die. So we just stopped doing it. We all got together as the world and we said, we're not gonna manufacture CFCs anymore. And the problem got fixed. And we said, yeah, it's mostly fixed. It's gotten a lot better. I can show you some pictures later. Yeah.
Where is it located?
So we can not go there.
Yeah.
Well,
Go there.
mostly over the south and north pole, ozone tends to collect in the polar, the polar regions. But it's mostly fixed now, so you can go if you want.
Mostly, but it's
A lot better.
it does.
Okay, does this make sense? Does that nice analogy work for you in your brain now? Ultraviolet dissociates, right? Breaks it apart. So just like we're dissociating, okay? Same thing's happening here, but it's ultraviolet light. Okay? And then down here, this is what we like. We like visible. We want that to get through the atmosphere because it lets us see. Lets us find the strawberry, lets us find the nice rabbit. Okay? And sometimes it's small enough that it bends off of oxygen, for example, and maybe it doesn't go exactly the way that we thought it would go. So red is going to go straight, but sometimes blue bends a little bit more. We'll talk about that in more detail. Visible, mostly, gets through the whole atmosphere. Over here, though, infrared absolutely loves water. Best friends with water. As soon as infrared sees water, they want to hang out. Okay? And they want to go dancing together. You see the dancing? So they go and they start spinning together. They start moving their little arms together.
That's boiling.
No, that's just like dancing. It's just like energetic. So I'm oxygen and these are my hydrogen. And it's like, wee. Okay, that's what happens to water. Okay, and that's infrared. You get it? So you fully understood this now, right? 100%. What's the top one do? It kills. Yeah, ionized breaks it apart.
That's great.
This one.
Breaks.
Break apart the molecules.
Why are they different?
Well,
Who are we dissociating?
molecules.
Which ones? What's the point of all my storytelling?
Oxygen.
Very close.
Also,
Ozone. Very close. Yeah. Ozone is the one that we care about here. This one, anyone. I don't care. Random killers, serial killers, right? This one? No, this one doesn't kill anyone. It's a gentle baby. It's good. It mostly goes right through the atmosphere, right? This one likes to dance with water. Okay, so now we do in fact understand it fully, right? Okay, so now this will allow us to understand the structure of the thermal structure of the atmosphere. So at the very bottom, this is where we live. Okay, as we go up in altitude, different types of light don't get absorbed, right? So up here is where the satellites we live in. This is where Mount Everest is. Okay. This is where like the tallest balloons are. And these are the ones that we shoot down. This is like a typical cruising altitude. Okay. You want to fly in like this cruising altitude because you don't want to be too high, right? It's scary. You want a lot of like air to protect you. You don't want to be too low because you don't have to go through too much air. You just want to be in there. And you don't want to hit a balloon. Okay. So we said that the visible mostly makes it down to the surface. Hey, that's true. This diagram didn't lie. The ultraviolet gets absorbed here by ozone. Ozone specifically. Okay. If I didn't have ozone, what would happen to ultraviolet?
Straight through.
Go right through, and it would cook us right here. Yummy. Okay.
That's a TV.
Okay. And then the X-rays, as soon as they get dense enough, they just start dissociating anything they'll find. So they're the first ones to stop. Okay. Now you'll notice here, at the bottom it's warm, and then it cools off. And then it warms up again. Oh, that warming in the middle atmosphere is coming from UV absorption by ozone. Oh my goodness. And now I keep going. It starts cooling again as I go up. And then I heat up again because X-rays are heating me up. Oh, at the bottom, who was heating up? The visible sunlight that gets all the way through and then gets re-emitted as infrared. There's water down here. So it starts bumping into the water, gets us really warm. And you keep this nice little pocket of hot, warm gas, traps and heat it. Okay? Okay, so let's talk about all of the different parts here. We live in the troposphere. Okay, that's that bottom part. The temperature drops with altitude as we go up. We can see that because we can see snow in the mountains. This is probably the only time that I've ever said that in class. Okay? It's warmed by infrared light from surface and convection. So this visible light gets absorbed, then gets re-emitted and reabsorbed, and re-emitted and reabsorbed. Note that the visible light here is not heating the atmosphere. It heats the ground, and the ground gives off infrared, which is then absorbed in the atmosphere. This is important because what is the hottest time of the day? It is not noon.
It's like around 4, like 3 o'clock, right?
It's about 2 or 3. So it lags behind noon because the ground has to heat up. And then once the ground heats up, then it starts emitting in the infrared and it heats up the atmosphere after. Yeah.
Is it the same scenarios for like when it's like nighttime? Like I was like the coldest around like 6 a.m.
It's actually about 3 p.m. Oh, I'm sorry, 3 a.m.
Oh.
But it feels coldest because we're not used to that, right? Okay. All right, and if you look at your weather app tonight, see that I'm right-ish. Ish. Don't put too much stock in it. Okay. Don't look at it right now, Kobe. Okay, so let's talk about the stratosphere. That's the next section. So this temperature rises with altitude in the lower part and then drops. And we already said that this is warmed by absorption of ultraviolet sunlight due to ozone. So I get rid of ozone, and then what would I have in here if I were going to draw the thermal curve? Do I still go this way? Okay, let's say I get rid of all the ozone. No more ozone in the atmosphere. And now I want to connect this point to this point. You go this way? This way?
I think the surface would be hotter.
Oh, this is gonna become a hungry. I'm excited. Okay, I'm not even gonna answer that anymore. All right. Okay. So this part at the very bottom, and maybe I should have done this one slide ago. This part at the very bottom is a process called convection. We've seen convection before, right? We've seen it in boiling water. So you have hot on the bottom and cold on the top, and you want to transport that through a gas or a liquid. And so you do that by heat on the bottom comes up, form of bubbles, and then this cools, and then it sinks, replaces it like that, makes little circles. Okay. Come on now, come on now. I don't have time for you. Okay. That's enough. Based on the plot, can convection occur in the stratosphere? Is it A, yes, from 10 to 50 kilometers? Is it B, yes, from 50 to 80 kilometers? C, yes, only at 50 kilometers? Or D, no? And let's recall, this is the stratosphere. Don't look at these. That's this. You know when you're ready? Let's vote on 3, 2, 1. Okay. Okay. Why don't you ask your neighbor? Because it seems like no one agrees. Okay, we ready? Okay, let's vote on 3, 2, 1. Okay, all right. Someone on this side was very successful because you're all the same now. But this side is still very undecided. I want to argue their point. Yeah.
Okay, so, on the troposphere, instead of going from hot to cold, right?
From where?
Going from hot to
Here?
cold, yeah,
Oh, if it gets colder as it goes up.
yeah, and then.
Okay.
And then, once you hit the stratosphere, it starts to get cold, but then it goes back up, right?
Oh, okay,
So then from 50 to 80.
50 to 80.
Yeah, since you need it to be hot to cold, right?
But you want it to be hot on the bottom. And that hot stuff wants to rise. And then it cools and it comes back down. Can I do it here? No, because stuff that's hot down here just rises to where it wants to go. And it just chills. So the only place that I can get convection is down here and right here. What about up here?
30 edge.
Yeah, can I get convection anywhere in here?
Because if it gets hot enough, it will just leave, right?
Yeah, if it gets hot enough, it'll just leave. That's correct. Okay, all right, so that's all for today. We're gonna talk more about atmospheric structure, and then we'll look at very specific cool things about each of the planetary atmospheres, including why we have air to breathe. Cool, fun thing. And then we'll do Jupiter's atmosphere, which is sick, and Saturn's atmosphere, which just looks beautiful. You won't even learn anything. It's just like, wow, that's cool. Okay. All right. Caesar, can you hit those lights?
Here's the one thing I saw online,
Mhm.
and I barely even read it,